All right, welcome. Today we are going on an absolutely wild journey. A journey to the very edge of time itself, and maybe, just maybe, a little bit beyond. We're going to dive into loop quantum cosmology, a theory that asks a mind-bending question. What if our universe wasn't the first?
I mean, really think about that. Is this it? Was our Big Bang the one and only beginning, the ultimate starting point? Or could we just be the latest chapter in a much, much longer cosmic story? For the longest time, that question was pure philosophy. We had no way to test it. But now, that's starting to change. Clues are emerging from the oldest light in the cosmos itself.
So, what you're looking at here is the cosmic microwave background, or the CMB for short. It's basically a baby picture of our universe, the afterglow from the Big Bang, snapped when the cosmos was just a toddler, about 380,000 years old. And for the most part, it's an incredibly smooth, almost perfect picture. But here's the thing. When scientists looked really, really closely at this picture, they found something weird. Anomalies. Glitches in the pattern that, according to our best theories, just shouldn't be there.
So, just how weird is this glitch? Well, statistically, it's a 3 sigma event. Now, in the world of science, that's a pretty big deal. It's the kind of thing that makes you sit up and pay attention. To put that in perspective, it's like flipping a coin and getting heads 8 times in a row. It's not impossible, right? But you definitely start thinking something's up with that coin. And in this case, it makes scientists think, maybe something is up with our understanding of the universe.
Okay, so what is this glitch exactly? It's something called power suppression. Basically, when you look at the temperature differences in that baby picture of the universe, the intensity of those differences on the largest possible scales is way weaker than our theories predict. It's like taking a photo of the brand new universe, and for some reason all the biggest things in the picture are just blurry, fainter than they should be. And that one little detail, well, it throws a huge wrench into our standard story of the Big Bang.
So, to really get why this one little glitch is such a headache for physicists, we've got to talk about our standard model of how everything began.
You know, Einstein's theory of general relativity is one of the most successful theories ever. It's amazing, and it lets us do something incredible. Play the movie of the universe in reverse. We see all the galaxies rushing away from each other, so we just hit rewind. They get closer and closer, and we keep rewinding as everything in the entire universe, all the matter, all the energy, space, and time itself, gets squeezed down and down and down until it all crushes into a single point.
And that point, that's what we call a singularity. And let me tell you, it is a complete and total brick wall for physics. It's a point of infinite density and infinite temperature where all our math just breaks. It spits out nonsense answers like infinity. It means our best theory can't tell us what happened at the beginning, let alone what came before it. The physics just stops cold. But what if? What if there was no singularity? What if the universe didn't start with a bang, but with a bounce? Now that is the wild and fascinating idea at the very heart of loop quantum cosmology. Okay, so loop quantum cosmology, or LQC, completely flips our idea of reality on its head. It says that if you could zoom in to an unbelievably tiny scale, the Planck scale, you'd see that space-time isn't some smooth, continuous sheet. Nope, it's pixelated. It's made of these discrete, indivisible quantum atoms of space itself. It has a fundamental graininess to it. So think about it like this. With general relativity on the left, there's nothing to stop that infinite collapse into a singularity. But with LQC on the right, those fundamental pixels of space can only be squeezed so much. As a universe contracts, this quantum geometry starts to push back hard. It creates this incredibly powerful repulsive force, and it means the singularity can never, ever form. And the result? No Big Bang. Instead, we get a big bounce. So picture this. A previous universe collapses in on itself. The density gets absolutely insane. It hits this maximum limit called the Planck density, and then bam! That quantum repulsion kicks in and forces the whole thing to rebound. And that rebound, well, that's what we experience as our Big Bang.
Okay, a bouncing universe is a super cool idea, right? But here's the million-dollar question. Does it actually explain that weird glitch we saw at the beginning? That strange anomaly in our cosmic baby picture?
Right, this is where it all comes together. If there really was a universe before ours, did it leave any fingerprints behind? Well, loop quantum cosmology says absolutely yes. And the crazy part is, it predicts we can actually see them in the sky today.
Let me try to break this down.
In the standard Big Bang model, all the waves and ripples in the early universe get created after the bang happens. But LQC tells a totally different story. It says the biggest, longest waves, the very ones that correspond to that glitch we see, they were already there before the bounce. They were so huge they were actually bigger than the curvature of the universe at the time. And because of that, the unique physics of that pre-bounce era kind of dampened their energy.
And here's the punchline. Those super long, dampened waves from the old universe, they actually survived the bounce. They were carried right through into our universe, leaving behind this very specific echo, a suppression of power on the largest scales that just so happens to perfectly match that 3 sigma anomaly in our data. Suddenly, the glitch isn't a glitch anymore. It's a fossil. It's a message in a bottle from a universe that existed before ours.
Now, this is super important. This isn't just some cool sci-fi story that sounds good. LQC makes real, concrete predictions that we can actually go out and look for with our telescopes.
So we've already talked about the first prediction, those weaker temperature spots on the biggest scales. But LQC goes even further. It also predicts very specific patterns in the polarization of that ancient light. Think of it like the orientation of the light waves. And the real killer prediction, the one that would be a total smoking gun, is a unique suppression in what's called the EE correlation signal. If we find that specific signature, well, that's an echo from before the bounce that other theories are going to have a really hard time explaining away.
And this is what is so profound about all of this. It means we're starting to have, as the researchers put it, a two-way dialogue between quantum gravity and observations. We can literally use our telescopes to test ideas about the fundamental pixels of reality itself. It's just mind-blowing. So, what does this all mean? The next time you look up at the night sky, think about this. Could it be that the answers to the biggest questions about the cosmos aren't just out there in the stars, but are actually hidden in the tiniest possible pieces of space and time? A quantum fabric that actually remembers a universe that existed long before our own? It's an incredible thought.